sorry, it's should be a vector. Let's assume it's just a vector, right? And that's supposed to equal the integral of this volume V as a function of time. So V as a function of time just means like what I've just said. The density is changing, so the volume is also changing because of the conservation of mass. So we're interested in a changing volume, but encompasses the same amount of material. So that's dg by dt plus g times the divergence of u. U is the velocity, right? And dv. Now this is the Reynolds transport theorem. And if you want the proof of this, the proof is given by, so this equation is 6.6a in uh, the book Elementary Fluid Dynamics by Atchison. Right. And this and the proof of that is given in the solution of exercise 6.5 in that book. The good thing about this book is it provides solutions, although not very detailed solutions, in the back of the book. But although it's not detailed, it's helpful. Okay, so I'll just clear the board and so let's use the Reynolds transport theorem, setting G equal to rho u. So that's the momentum density. Now you have d by dt v of t, right? Rho u dv. Right, I'll just use the small d instead of big D. Total derivative, material derivative is the same thing. And then the right-hand side equals to, you have the bracket d rho u by dt, right? And normally if you think naively, then that's just dv and it's done, right? Oh, actually, I used the big D, so I'll just use the big D here to make everything just consistent. Right. Naively, you would think that will be true, right? That's also integrate over Vt, but in fact, it's not. And there's an extra term. This extra term is plus rho u times divergence of u, and that also, and that again dv. So let's just expand the right hand side. Still integral v of t. Then you have rho du by dt plus u d rho by dt. Right, and plus rho u divergence of u dv. Now equation looks even more complicated, but if you use the continuity equation, which is easily derived in the lectures, so I'll just take it for granted. Partial u partial t plus divergence of rho u is 0, and that means partial rho partial t plus u dot grad rho plus rho actually is equals to minus rho divergence of u, right? So we're not assuming incompressibility, we're just treating a completely general fluid. Now, the left-hand side is just d rho by dt, right? So you will see that, okay, when the material derivative of rho is 0, then you have divergence of u is 0, and you have incompressibility. But if you don't have this incompressibility equation, this still holds true, and divergence of u would be 1 over minus rho times the material derivative of rho with respect to t. Now, if you substitute this into this, you will find that this is equal to integral over v of t rho du by dt plus u, and it's not a plus again, it should be a minus here, because you have a minus sign here, right? So this minus rho means u rho divergence of u. Now plus here is also a u rho divergence of u. Now you will see where the convenience come from, and this whole thing dv, you will find it's just rho du by dt dv, right? So that arrives at the same result as like my previous argument, which is that because rho dv is equal to dm and is constant with time. So so we have this expression. So these two things just come to the same conclusion. But of course, if you find that argument a little bit more hand-wavy, you can go through the math and do the Reynolds transport theorem and still find out that this rho is left out of the material derivative, and still representing the most general case.